So, we see about the design criteria which is being used for the transmission insulators. Very important is the insulation coordination, which the high voltage engineers have to be careful while designing the insulation, particularly for the EHV and UHV transmission levels. So, insulation coordination mainly aims at selecting proper insulation level for various voltage stresses in a particular rational manner. So, that is its main objective is to assure that insulation has enough strength to meet the stress on it. In case of the stresses which we discussed, maybe mechanical, maybe electrical, maybe environmental, the insulation has to withstand during emergencies conditions. So, to see all equipments which are to properly protected, so it is desired that insulation of various protective devices must be properly coordinated. This is the main aim of insulation coordination. The graph which is shown here, it gives the voltage versus the probability density over voltages and insulation flashover. Simple looking into the insulation aspect of any particular equipment, this is the insulation strength which is designed for the equipment or the component. This shows the stress which is being continuously on it. So, the level of the coordination or the insulation coordination will definitely be seen that it has more strength compared to the stress which has to undergo in the field because of several stresses which is likely to face. So, the maximum over voltages as we know occur rarely, and likewise insulation strength occurs very rarely because insulation strength rarely decreases to its lowest value. This has been in practice which has been seen. So, the likelihood of both the events, that is the over voltages occurrence and also the insulation strength decreasing simultaneously is a very limited and very rare event. Therefore, considerable economy may be achieved by recognizing the probabilistic nature of both voltage stress and insulation strength by accepting a certain risk of failure. So, this is where the design aspects looking into the economic point of view have to be taken care. So, this leads to a substantial decrease in the line insulation if you properly design, properly take care of the parameters, particularly the spark distances, the dimensions of the tower, the weight of the entire insulator string consisting of the conductors, accessories, corona control links, so on and so forth. Then right of way, the clearances of the right of way resulting in the decreased cost of line. So, this proper coordination, proper planning, proper insulation design will help in the decrease of cost of the line, and this decrease in line cost must be seen again as the increased risk of failure and the cost of such failures. So, the design engineers have to bear in mind while designing proper insulation, either it is not required to over design the insulator or under design the insulation. So, the cost must be weighed against the risk of failure and the cost of the failures which may happen in the system. This is an important insulation coordination curve which shows the peak kV peak of flashover voltage with the volt time curves, this versus the time. You can see that various curves are there. These are the level of protections which are being done for the insulation level. The initial, you can see the A, B, C, D are different curves here, the insulation level. Example, for the transformer, the line insulation will be somewhere here. To protect the transformer, we have a LA, that is a lightning arrestor, which has a lower insulation level than the transformer. So, in case of over voltages, in case of failures, in case of abnormal conditions, the initial sacrificing should be a lightning arrestor, where the lightning arrestor should conduct in the transmission system and protect the transformer. So, this is how the line insulation is designed. Further, the transformer, there may be some other insulation which has been designed like the bus bar and so on and so forth. So, the insulation coordination, proper planning proper insulation coordination is to be done to protect the major equipments, particularly the transformer, the circuit breakers and controls in the substation and for the generating in the transmission network. So, earlier I mentioned about the over voltages which are likely to be seen in the power system network. So, temporary over voltages, again these temporary voltages are lightly damped oscillatory type of voltages at supply frequency. I was telling it normal 50 hertz frequency, the over voltages are likely to happen and these are known as temporary power frequency voltages. So, switching over voltages or switching surges, these are damped oscillations at frequencies of less than 10 kilohertz. Again switching over voltages are likely to occur because of the opening or closing of the circuit breakers in the system. The switching over voltages typically have a wave shape of 250 microsecond to 2500 microseconds. So, switching over voltages as I was mentioning are damped double exponential oscillations which may at frequencies less than 10 kilohertz. The switching over voltages are of in this nature where the front time will be somewhere around 250 microseconds and the tail time is at 2500 microseconds. The time for front to time to tail is 250 by 2500 microseconds. These are normally happening because of the closing and opening of the circuit breakers in a transmission system. Then coming to the lightning over voltages, these are again damped oscillations at frequencies which are less than 100 kilohertz. These lightning over voltages may occur due to the natural lightning which may strike the tower or which may strike the equipment. So, these natural lightning will be of the front of 1.2 microseconds and a tail time that is 50% of the magnitude is the tail time. This is V50 microseconds. So, lightning impulse is 1.2 by 50 microseconds whereas switching is 250 by 2500 microseconds. So, these over voltages are occur in the power system and proper protection for these over voltages have to be taken into consideration. So, this table shows various over voltages which what we discussed which may occur because of the external or the internal applications or internal service conditions. So, the external is because of the lightning as we were mentioning. So, natural lightning will create a direct induced or a back flashover. These aspects will create various types of impulses, various types of over voltages on the transmission network. Then the second external being the NEMP, that is nuclear electromagnetic pulse. This is because of the nuclear accident which may happen. So, which creates a very sharp pulses and may create a problem to the transmission network. So, non-nuclear electromagnetic, third external over voltages being the non-nuclear electromagnetic pulse, this may be because of the magnetic solar storms or so on so forth. So, the second being the internal operations of the power systems can cause the transient over voltages. This transient what we were talking about is a surge or the switching over voltages which may happen because of the closing and re-closing, that is opening and closing of the lines or interruption of capacitive or inductive currents or switching on transformers or fault initiation or clearing of the fault. So, these aspects may create a transient or a switching surge voltages in the transmission network. And internal again at temporary over voltages, these temporary over voltages may occur because of the load rejection, because of the Ferranti effect, which the sending end and the receiving end voltages differ. So, the Ferranti effect also will cause a temporary over voltages, then self excitation because of the saturation effect, because of the ground faults and some asymmetric faults. So, all these are likely to cause the temporary over voltages in the system. The third internal over voltages may be because of the steady state operations also. So, these steady state internal over voltages may occur because of the contact with circuits at particularly of higher voltages, maybe because of the neutral inversion, the arcing which is happening in the ground side, that is the arcing ground phenomena, and the resonance phenomena. So, these are various classification of over voltages in the power network or a power system have to be contained to see the proper functioning of the equipments which are used in the transmission or the distribution network. So, we have looked into the slides. So, very important, this gives us the idea what are the factors which determine the design for insulation. So, the voltage levels particularly lesser than 4 kilovolts, we have to look into the mechanical clearances from the ground, the towers which are being used have to be looked into the mechanical clearances. Below 4 kilovolts, not much of the lightning switching surges play a role. So, above 4 kV to 33 kV or 34.5 kV, the corona and the lightning surges play a role in the design of line insulation. So, the corona discharges which can create insulation breakdown, particularly at that voltage levels, which may generate because of the transmission conductors, the hardware, the insulating accessories, and also the lightning surges which may dominate during this voltage. The insulation design engineer has to keep in mind the various factors which are responsible for the design at a particular voltage levels. Coming up above 66 kV to 220 kilovolts, we have to look into the consideration of lightning and switching surges which we previously looked. So, lightning is again a natural phenomena, switching surge may be happening because of the transmission network closing and opening of the circuit breakers, so on and so forth. So, the design has to be taken care for lightning and switching over voltages up to 220 kilovolts. Above 220, that is extra high voltage 400 kV to 400 kV level, which we normally call at extra high voltage levels, and ultra high voltage levels above up to 765 kV or 800 kV. Apart from lightning, the switching surges and the contamination or a pollution dominates on the insulation design. So, the insulation engineer has to take care of the switching surges, the contamination or a pollution above up to 765 or 800 kV. Further, ultra high voltage insulation design mainly depends on the contamination aspects. The contamination or the pollution is a very important aspect to be considered for the design above ultra high voltage insulation. So, for EHV, UHV, that is extra high voltage or ultra high voltage, pollution or a contamination performance is a very important aspect for the design of line insulation, and we will be looking into this contamination, how serious, how it happens, the physics behind the contamination. So, we were looking into the electrical aspects. Now, the design criteria which is followed for the mechanical aspect. So, its primary function is to support the line, the insulator string is to support the line mechanically, one of the important factor apart from the electrical isolation. Mechanically it has to support the tower. So, we have to estimate the maximum load which an insulator string consists, including the insulators, the line conductor, the accessories, the hardware, and the design has to be done how the load, the maximum load including the insulator string will see under normal and also overload factors. Overload again depending upon the dynamic overloads or because of the compression, because of the tension aspects, or because of the heavy winds and so on. So, this has to be kept in mind before designing the requirements for mechanical criteria. So, the mechanical properties of dielectric component of high voltage insulators, typically when we look into that, the mechanical strength of porcelain is somewhere around 30 to 100, and for glass it is 100 to 120, and polymer it is 20 to 35, and resin bonded material is 1300 to 1600. Resin bonded glass fiber RBGF used for core of the polymer insulator, which we were talking about, the fiberglass rod which is employed for the polymer insulator core. So, resin bond glass fiber withstands a tensile strength of 1300 to 1600, and in case of compression, the mechanical strength requirement for porcelain is 240 to 820, the glass being 210 to 300, polymer is 80 to 170 and 700 to 750 in case of the polymer or the resin bond glass fiber. So, what this mechanical criteria, particularly for porcelain or ceramic insulators, when the porcelain begins to cracks, it electrically punctures, that we have to keep in mind. So, the mechanical strength may deteriorate the insulation initially, this will lead to the electrical punctures. So, we should not exceed, or the utility should not exceed 50% of the mechanical and electrical rating of the insulators. So, this has to be checked for cantilever rating, which do not exceed more than 40% of the actual load. In case of polymer insulator, non-ceramic insulators, the load should not be beyond the specified mechanical load. For each type of voltage level, the specified mechanical load is being mentioned. Similarly, specified tension load, a routine test load, and a rated cantilever load. All these things which have been mentioned will be applicable for a particular voltage level, particular insulator. Dimensions have to be strictly followed, so that the failure does not occur and the insulation does not weaken in the system. The important component while designing the electrical criteria is the strike distance. What is the strike distance or a dry arcing distance, which is known with the high voltage terminology? The strike distance or the arcing distance is the shortest distance through the surrounding medium, that is a surrounding medium near the insulator between the terminal electrodes. You can see here, this is the insulator can be of porcelain, ceramic, glass or hollow insulator. A representation here very clearly is the both, here the end fittings are of metallic end fittings. The distance between the end fittings from here to the end fittings, in between there is a complete insulation. So, this distance, the direct distance, the clearance from the metal to the metal is known as the dry arcing distance. So, in case when one of that is connected to the high voltage, other is connected to the ground, because of the voltage stress increase, the likely to flashover and the nearest flashover will happen during this metal to metal junction. So, that the shortest distance through the surrounding media, that is air surrounding media in here, should be from the terminal electrodes. So, this is known as a strike distance for a hollow or a porcelain bushing. Similarly, in case of insulator string, a representation of 3 insulators is given. You can very clearly see that from the top cap, the metal cap to the bottommost metal pin, this is the arcing or a dry arc distance or a strike distance which is being referred. So, the dry power frequency, PF is the power frequency flashover and impulse flashover based or designed on the importance of the strike distance by the installation or a design engineers. So, the power frequency voltages and impulse flashover voltages are likely to see depending upon the dry arc distance which is being provided, and wet flashover also. See, in case of the insulator there is a rain, because of the wetness of the wetting of the insulator surface, the flashover voltage is likely to come down. So, this flashover voltage is also kept in mind while designing the arcing or a strike distance. So, the leakage distance mainly helps to maintain the surface resistance of the strike distance. So, this is a important design criteria for the electrical. So, very clear distinction has to be made between the strike distance and why it is important in the design of insulation. So, next is the leakage distance. What is the importance of a leakage distance? So, this is an example of the insulator string which consists of several insulators, double tension insulators, several insulators are there, and here you can see this metallic ring type of arrangement are known as the arcing horns. So, this distance between this is known as the strike distance, what we discussed earlier. The tip of this metallic to the tape is the strike or the arcing distance which is being maintained for this insulator string. In case of over voltages, the discharge should happen from metal to metal and it should go to the ground. So, where the protection for the insulator's string is done. So, similarly, what is leakage distance? The leakage distance is the sum of shortest distances measured along the insulating surface between the conductive parts as arranged in here. So, this shortest distance, each insulator, each ceramic portion minus the metal parts, that is the cap and the pin, will constitute a leakage distance. The actual insulation provided for entire string minus the metal parts will give you the leakage or distance for the insulator string. Here we have to take from the first petticoat of the insulator on the surface here and again from here. So, this addition of this porcelain insulation will give you the leakage distance of any insulator string. So, as discussed, we were looking into we were talking about the over voltages which happen in the transmission. So, here are few examples which have been given. The first is the lightning impulse or a lightning surge which occurs in the transmission, how it looks. The second is the lightning impulse chopped wave, and third is the switching impulse. So, we will look one by one. The first is the full lightning impulse voltage which is being shown without oscillations or overshoot. Typically this is a textbook type of waveform which is been shown, but practically you may happen to see the oscillations here in this rising portion. So, here it is not been shown to see that how it is being constructed. So, the full lightning impulse without oscillations which is shown here is from the 0 to the 1 where it shows the magnitude, and the time to front is calculated either from the 10 to 90%, in some cases it is 30 to 90% depending upon the oscillations which are seen here. So, the time to tail it is taken as the total magnitude, that is a 50% of that gives you the time to tail. So, that is a typical lightning impulse or a lightning surge waveform which is used for the application of the various components to check their performance in the laboratory before it is being used in the transmission system. Similarly, you have a lightning impulse chopped. So, this again a similar waveform, the chopping is intentionally done either on the tail or on the front. So, in the transmission network these type of surges are likely to see across the transformer or any other equipment. The intention is to simulate such conditions in the laboratory and check the insulation could withstand in the laboratory. So, that is where the chopped lightning impulse is being carried out. Again there are standards for this, how many applications of lightning impulse voltages, whether it is 10 positive, 10 negative or 10 positive of this thing and 10 negative, it depends for each component. Standards have been specified for these applications. Based on the standards, the performance is verified in the laboratories before it is being used in the field. So, here again this waveform shows the chopping in the tail section, and similarly the chopping could also be done in the front portion. So, various type of lightning impulses which will be intentionally chopped at a required level will be tested for the insulation. The third is the switching impulse of over voltages or a switching surge what we call. Here as I mentioned earlier, the time to front will be 250 microseconds and the time to tail from here to the magnitude 50% of the magnitude will be 2500 microseconds. The switching surges are likely to happen because of the closing and opening of the circuit breakers and in the transmission network. Here the front time will be 1.2 microseconds and tail time will be 50 microseconds for lightning surges. For switching it is 250 by 2500 microseconds. So, now we come into the selection of a suitable insulator, how to design or select an insulator for electrical for various levels in the before it is being put in the transmission. A thumb rule has been given here. Design aspect consists of several aspects before it is being put in the service. As a thumb rule, just for understanding, I have given you here the selection of how a suitable insulator is made for the transmission system. A simple example here I have given for two voltage levels, that is 66 kV and 240 kV. Similarly, for higher the voltages could be used with the factors which have been employed will be slightly different. So, a simple example for a 220 kV system voltage, the 220 kV, the highest system, consider that second portion of the column, the values in the second portion. The 220 kilovolt transmission system is a normal operating voltage will be 186 and the maximum operating or the design of insulation for a 220 kV will be done to 245 kV. So, this is what I have shown here. The system highest system voltage of a 220 kV is 245 kV and the system line to ground voltage, that is whatever I have indicated in the A, the system line to ground voltage divided by root 3, that is 1.73 into 1.05, there is a 5% extra is taken into consideration for design, it gives 170, value is 170, this will be using it later. So, further peak of line to ground voltage is nothing but the value which you have got is 170 into root 2, that is 1.414 gives you 220.5 is the number which you obtain for line to ground. So, this how the electrical parameters are calculated. Further, the leakage distance, how leakage distance is calculated. So, for leakage distance we have to consider where the transmission line or a transmission tower is being erected. So, that is very important. I was mentioning you various type of pollution zones exist. If it is the pollution zones as per the standards or a pollution levels is classified into very or no pollution level, very clean level, then there will be a light pollution, a moderate pollution or a heavy pollution zones. So, the transmission lines passing through different zones while calculating the leakage distance have to bear in mind about the factors to be considered. So, in case your transmission tower is running near a moderate pollution zone area, the factor of 1.5 to 1.7 is considered. Similarly, if it is high 2 to 2.8 is considered. So, next after the leakage distance, the insulator minimum leakage distance is calculated simply with the help of 170 is the B is 170 into the inches per kV, that is simple. For a 220 kV it will be 170 inches, that is the leakage distance which I have converted into inches per kV. Sorry. Then for calculation of switching over voltages, a factor of B, that is again 170 is taken and multiplication factor in particularly for 250 kV and lesser, somewhere the factor will be 3 to 5. I have assumed 5 as the factor, multiplication factor. So, 1 for 220 kV the B is 170 into 5 gives you 850 is the switching surge voltage level for a 220 kVA system. This is all the thumb rules which have been indicated here. Next, for calculation or designing for lightning over voltages, this simple formula is considered here, where the current is the resistance and the value of PV is taken for the calculation. So, typical value of current in case of lightning strike, it is taken anywhere between 2 to 50 kilo ohms for a transmission system, and during that period the resistance is likely to be anywhere between 10 to 20 ohms. So, for a 220 kV system, I have considered a 44 kilo amps, somewhere 19 ohms plus 220 kV approximately. This gives 1056 kV if you want to maintain the insulation level for lightning over. For switching it is 850, for lightning 1056 kV. So, when you summarize the system requirement with approximate value for a 220 kV system, you see the leakage distance should minimum be 170 inches, the switching surge voltage should be 850 kilovolts, and lightning impulse withstand voltage should be 1056 kilovolts. So, these are the values which you obtain, or a design engineer is likely to look into these aspects. As the voltage level goes up in case of 400, 765, 800 kV, a similar exercise will be done much before the insulator, and also apart from this several other considerations will be taken into consideration.